I'm Tip, and this is PCB Static. In the last episode, we talked about why RF traces need to be 50 ohms. A lot of people, after learning this, feel like they've got it. They can calculate impedance now, so they think they're already RF engineers. Not so fast. The real pitfalls are just beginning, because today's topic is something where impedance is even easier to overlook, but it's also much more likely to cause your project to fail, and that is the return path. When a lot of people first get into RF, the picture in their mind looks like this. The signal comes out of the chip, passes through, reaches the antenna, and that's it. Mission accomplished. Time to clock out. But in reality, it's not like that at all. All current must form a loop. If it goes out, it has to come back. Otherwise, that current simply doesn't exist. So an RF signal isn't just a single line, it's an entire loop. The outgoing path is important, but the return path is just as important, sometimes even more so, because you can see the outgoing path, but a lot of people never even think about the return path. So here's the question. How exactly does the return current flow? Can it just take any random ground line back? Now, especially not at high frequencies. It's actually really lazy. Just how lazy? It always takes the shortest, tightest, and easiest route. In engineering, this is called the minimum inductance path. It sounds pretty high tech, but it's actually easy to understand. Imagine you're heading home from work and your GPS gives you two routes. One takes 10 minutes, the other takes 40. Which one are you going to pick? Of course, you'll choose the 10-minute route. The return current works the same way. If the reference ground is complete, the return current will stick right under the signal line, like hitting all green lights along the way. It gets there directly, and the performance is the best. Next up is a classic pitfall in RF design. A lot of engineers have done this when routing traces. Hey, there's a gap in the ground plane here. No big deal. As long as the trace can get through, it's fine. But then things start to get mysterious in the project. Why? Because the signal does make it across, but the return current is left dumbfounded on the edge of that ground gap. Like, bro, how am I supposed to get across? So it has no choice but to take a detour. What used to be a highway route now turns into a trip around the ring road. Originally, the return current area was very small, but now it's expanded more than tenfold. Congratulations, you've just made an antenna for free. As a result, EMI increases, reflections increase, and impedance gets worse. Performance drops. There's a golden rule among RF engineers. Never let RF traces cross over different reference planes because your PCB won't warn you, but physics definitely will. Continuing with that navigation story from earlier, imagine you're on your way home. The road ahead is closed, there's construction behind you, and the bridge is out too. The navigation keeps frantically recalculating your route. Frustrating, right? That's what return current goes through every day. A complete reference ground is like a straight, high-speed highway. Smooth sailing all the way. Low inductance, low loss, high performance. But when you slot, hollow out, or cut the reference ground, it's like having roadwork all over the city. The return current has to take detours. In the RF world, there's a harsh reality. Taking detours means performance drops. So the most important value of a complete reference ground is to minimize the hassle for return current. Now, let's look at a question that many people are curious about. Why do so many RF boards have rows and rows of densely packed vias? People seeing this for the first time often ask, do manufacturers charge by the number of vias? Actually, that's not the case. These vias are like bridges on a highway. When switching between ground planes, the return current needs to quickly change its path. These vias are built specifically for that. Without vias and fences, the return current has to recalculate its route. With vias and fences, the return current gets a green light all the way. So these vias aren't just for decoration, they're insurance. This is especially important near antennas and connectors. It's also crucial near layer transitions. A lot of digital boards like to do it this way. They think leaving the ground layer empty or just running a few random traces isn't a big deal. But in the RF world, it's completely different because the greatest value of the reference ground is to provide a highway for the return current. If you cut slots or run traces and drill holes through it, it's like breaking up the highway. The return current gets jammed again, leading to reflections and radiation. This leads to worse S11 loss. So remember this, for an RF ground plane, the most important thing isn't the routing, it's keeping it intact. Today, we just need to remember one thing. RF current wants to go home too, and it's especially picky. It always wants to take the shortest, tightest path, the one with the least inductance. If you build it a highway, you'll get great performance. If you build it a maze, you'll get EMI. It's that simple. So keep the reference ground intact, avoid crossing splits, make reasonable ground cuts, and minimize the return current area. If you do these four things well, your RF design will already be ahead of many beginners. Thanks for watching.